This unit is one of the most important units that we will go over this year. It's foundational for a lot of different calculus that we will do throughout the course of the year when we learn about derivatives. Now, I've talked about this slightly before when we talked about the slope of the tangent line. That is the instantaneous rate of change. That's how these are connected. And so we're going to go through and define what a derivative is, and to find exactly how to get the slope of the tangent line. I found a couple videos. This first one goes pretty quick. The second one has some quote-unquote celebrities in it, but I think it does a pretty good job explaining how this works. And I'll pause it and talk through it a little bit, but here's what you'll kind of see. So here we've got some animation, which is I think is kind of cool, where they show lots of different tangent lines for this particular curve.
This is the fundamental of calculus. As we move along the curve, we are not just able to find a tangent line touching at...
So all of these, the orange lines, are the tangent line to this green curve at a given point.
At a specific point, but more importantly, we can find the instantaneous rate of change of that point. In other words, we are able to find just how fast we are moving along the curve. This has many beautiful consequences, but it is 100% due to what most calculus students disregard: the limit, which is why today I want to talk about the limit definition of the derivative.
Okay, so this is the limit definition of the derivative that you're going to need to know. And he's going to go through and explain it, and I'll stop along the way. But the long story short is this is just another way of looking at the slope of the tangent line.
It all starts with us fixated on a point x on the curve.
Okay, so if we find this x value, some random x value, its corresponding y value will just be f of x.
We will then choose another point on the graph that is h value away. There it is.
Okay, so here's what he means. We're going to go h units away. So if this is x and we go h units to the right, the new x is going to be x plus h. And so that x value, x plus 8, will generate a y value of f of x plus h. So we're going to plug that new x value into the f of x, and that will give us our new y value. That's where those points come from. And again, they could be anywhere on this curve. He just happened to put them there.
If you remember things from algebra class, we can form a line crossing these 2 points. This is called the secant line. We can find the slope of this line. That's great, but what happens when we start bringing these points?
Now, one of the things we've talked about the secant line and finding the slope of that line. But I think I've talked about this before. As those points get closer and closer and closer together, this secant line will, for all intents and purposes, become the tangent line. And that's what he's going to talk about now.
Ever closer together. Not good enough. Closer. Closer. In other words, we want this distance h to approach 0.
Okay? We want the distance h to approach 0, meaning we want the space between x and the other point to approach 0. We want that space to be infinitesimally small, and that's why we talk about the limit. X doesn't equal 0, or h in this case doesn't equal 0. It's going to approach 0 and get very, 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 very close, infinitesimally close. And that's how we can use the limit to help us figure this out.
So we take the limit of the slope as h approaches 0.
I mean, at this point, to the naked eye, this looks like the tangent line, but it technically is still the secant line because there is space between those points.
These 2 points are so close together they are basically touching each other, and essentially giving us the instantaneous rate of change.
Notice how he said basically touching each other. They are not touching each other, but they are infinitesimally close.
Change the function at that point x. This is the tangent line, and this is the limit definition of the derivative.
Okay, so the limit definition of the derivative, that's what I paused on before. Now this next video is where my quote-unquote celebrities are. It's definitely AI generated, and I don't know how you feel about the people in here, but I thought it was mildly entertaining, so I went with it.
Yo, define the derivative.
Let's slap two random points on this curve. Now, how do you find the slope between them?
I know the slope is y2 minus y1 over x2 minus x1.
Yeah, but to use that, it helped to actually know the coordinates of the 2 points you platform on.
We won't be too specific. We can say our first point input is just x, and so the output on this vertical axis is f of x.
Now we'll move along to the second point. We can say it's a distance h to the right, so we can label this input as x plus h.
And the output is just f of the input.
So here the output is f of x plus h.
So using that formula, we have f of x plus h minus f of x divided by x plus h minus x.
X plus h minus x is just h.
Correct. And if we make h ridiculously small, those 2 points will be pretty much in the same spot, so it'll give us the slope at a single point.
The derivative is what all this becomes when h gets as close to 0 as humanly possible.
Without actually being 0, though.
That's why it's called the limit.
Okay, so there you go. Infinitesimally close, those points get together. For all intents and purposes, then that it is the same point. So we take the limit as that distance between the 2 points approaches 0, and we're taking the limit of basically the slope formula. Okay, so that's what the derivative really is. It gives us the slope of the tangent line. The traditional definition, page 144, you can screenshot from here. One important thing to notice is this little prime. This means f prime of a. Okay, that stands for the first derivative. The first, yes, there's also the second derivative and third derivative, and we'll talk about that later. But this is the first derivative of f at a. So the first derivative of f at a, notice the x's went away now because we're inputting a for x. So this is the same definition that this guy had and also on the previous one. But now we've substituted a for x, okay? And this is, of course, if the limit exists. There's what's called an alternate definition, and this is more like the slope formula, all right? And so we have f of x, just whatever the y is. Again, notice the notation, f prime of a, first derivative of f at a, minus f of a, and then x minus a. So then as x and a get closer together, as x approaches a, this approaches a, this is starting to approach 0. That distance is starting to approach 0. Never equals 0, but it's starting to approach. Now, sometimes it'll ask you to use the definition. Sometimes it'll ask you to use the alternate definition. In the next problem, I'm going to show you both ways just to show you that it gives you the same thing, but you do not do both per problem, okay? I just want you to see it. So here's the problem that we're going to look at. Find the equation of the tangent line to the curve. Notice it says equation. It doesn't say find the slope. It says find the equation. So I have to have the slope, and they've given us a point. So I have a point, I find the slope, and then I can write an equation using point-slope form. So my function here, y equals the square root of 2x plus 1 at this point, and so you could graph this, and you could look at the point 4, 3, and draw a tangent line, but we don't need to do that, okay? We're gonna use both ways. First, we're gonna use the definition. Then I'm gonna use the alternate definition just so you can see that they, in fact, both work, okay? Now, we gotta get moving on this. So, what I'm gonna do here, in this case, in this problem, is since I'm plugging in the x value, a is 4. A is 4. And so f of a, so f of 4 is 3. All right, so I'm going to sub that all in real quick. So my input for this first part is 4 plus h, because a is 4. The second part is f of 4, and h stays h. F of 4 is 3. They give that to us, so I can replace this. And then I'm going to take this 4 plus h and put it into my equation 4x. This is my input value. So plug that all in, I get the square root of 2 times the quantity 4 plus h plus 1 minus 3, because f of 4 is 3. Now here we have one of those situations that we talked about in 2.3, where when I plug 0 in, this gives me 4 plus 0, which is 4. 4 times 2 is 8. 8 plus 1 is 9. The square root of 9 is 3. 3 minus 3 is 0. This top is 0 with direct substitution. The bottom with direct substitution is 0. So I have a 0 over 0 situation. So this is one of those cases where I have to use the conjugate in order to simplify this. And that basically is this but change the sign to plus, and I multiply top and bottom by it. Okay, after I distribute. Got ahead of myself a little bit. Distribute first. Now we're going to do that. Okay, so I've got 9 plus, the square root of 9 plus 2h plus 3, change the sign, and do it to the bottom. Now on the top, we're going to FOIL this out, but because this is a difference of squares, I know it becomes a squared minus b squared. Well, a squared is just, when I multiply these together, the square roots just go away. And the 3 times 3 just gives me 9, and then a negative times a positive is a negative. Square roots went away, 3 times 3. Now I've got 9 minus 9. And so I'm down to this. And as we've talked about before, the h's can cancel, which is good, because now this is no longer 0 over 0. Okay? So I've got 2 over the square root of 9 plus 2h plus 3. Plug the 0 in, so this goes away. The square root of 9, which is 3. All right. I didn't put the limit notation because I'm running out of space over here. So 2 over 3 plus 3, which is 2/6 or 1/3. So that is my slope. That is my slope. And that's the slope of the tangent line of this curve at this point. And so now that I know the slope and I have a point, I have enough to be able to write the equation. And so I just go ahead and use point slope, y minus 3 times 1/3 times x minus 4. Now I'm going to do the same thing over here. And we should get the same equation. Now here's where it changes. F of x is just the square root of 2x plus 1. F of a is still 3. And then I've got x minus 4, because that is my new a. Okay? So here's what that's going to look like. Again, the y, f of x, square root of 2x plus 1. F of a, f of 4 is 3. X minus a is 4. And notice how it went here too. So when I plug this 4 in by direct substitution, I get a 0 on the bottom. I get a 8 plus 1, which is 9. Square root of 9 is 3. Minus 3 is 0. We're back to a 0 over 0. So I'm going to have to do the same kind of thing over here that I did over here. So again, the conjugate is just going to be the same thing, but it's going to be a plus since this one is already minus to top and bottom. When I multiply the top out, these square roots go away, and this becomes minus 9. Okay, so then I can combine. 1 minus 9 is negative 8. And then I can't cancel yet. If I factor a 2 out of here, though, I'll get my x minus 4. And so now my x minus 4s go away, and I'm in a place where direct substitution is going to help me. Because the zeros go away. So I plug 4 in. 2 times 4 is 8, plus 1 is 9. The square root of 9 is 3. 3 plus 3 is 6. This is all 2/6. I simplify it a little bit more here. Okay, 2/6 or 1/3. And then, of course, I'm still using the same point. So this just proves that you can get the same equation 2 different ways, whether you use the definition or the alternate definition. Now, another thing that we talk about in this unit is velocity. And there's 2 ways that we can consider velocity. And one is using the secant line, like we did, like we've done in the past. And one is to find the instantaneous velocity. And I'm going to show you both ways. So first of all, to find the average velocity, we're talking about y2 minus y1. That's all that this is saying, over x2 minus y1. This is traditional slope. When you're finding the average velocity, you're finding the slope over 2 separate points. That would be the slope of the secant line. When you find the instantaneous velocity, we're talking about the first derivative. And that's what this is. The first derivative is going to give you that instantaneous velocity or the slope of the tangent line at that particular point, at that time A, okay? And so what's important to understand is that this is the derivative. The first derivative will give us that instantaneous velocity. And that is telling me the slope, the slope of the tangent line at a given point. That is the difference between these 2 things, okay? Sometimes the average velocity is a good estimate for the instantaneous velocity, but sometimes it's not. Okay? And so when we can find the instantaneous velocity at any given point or any given time, that's going to give us a better idea of how fast the object is moving at that instant. Okay. All right, here's our example. Okay, we've got displacement. Okay, that means change in position of a particle moving in a straight line is given by this formula. S often stands for the position. S of t, we'll see, is the position, equals t squared minus 8t plus 18, where time is in seconds. Find the average velocity over the interval from 3 to 4 seconds. This is not a point. This is saying from 3 seconds to 4 seconds, what is the average velocity? Well, what that means to do is find the coordinates of the point at time 3, find the coordinates of the point at time 4, and then take the slope. So in order to do that, I need to find the corresponding S value at time 3 and the corresponding S value at time 4. Now, the formula, of course, is always going to be given in terms of F, but in this case, the name of our function is S, not F. So I'm going to take S of 4 first, since it's the second point first, S of 4, I got to find that. Then I'm going to find S of 3, and then I'm going to just put 4 minus 3 on the bottom, okay? So S of 4, plug 4 in, 4 squared minus 8 times 4 plus 18, 16 minus 32, that's negative 16, plus 18, that is 2. So that is the Y value that goes with 4. Then I'm going to do the same thing for 3. Okay, so I have 3 squared minus 8 times 3 plus 18. This is 9 minus 24. That's negative 15 plus 18. That is positive 3. So now I have my corresponding Y values. So I'm going to go 2 minus 3 on top, 4 minus 3 on the bottom. Okay, there's my slope. And then this is negative 1 over 1. So my slope, my average velocity over time 3 to time 4 is negative 1. Now, what does that mean? Okay, what's happening to the velocity? I'll let you think about that. The next part is going to say, what's the instantaneous velocity at a given time? When time is 4. At time 4, what is the instantaneous velocity? Now, in this case, because I have the derivative definition, I only need one variable to plug in. Here we needed a couple, and we had to find some other things. We don't have to do that here. In this case, A is 4. So I'm just going to plug 4 in for A. Well, pretend that this part didn't happen and we didn't do this already, right? I would have to plug 4 in for 4 plus H for T, and I have to plug 4 in for T. Now I'm going to write it all out. That way it's you'd know what to do in a standalone problem. But in this case, we already know what F of 4, or in this case, S of 4 is. They really should be S's. Okay, we already found out what S of 4 is. All of this right here is 2. We already did that, okay? Now, notice I plugged 4 plus H in everywhere there was a T. Now, we're going to have to simplify this out, and I don't have enough room over here, so I'll go to the next page for that. All right. Now, the one thing I want to caution you before I do that, please do not tell me this is 16 plus H squared. This is the Batman meme that you know and you should be familiar with on my wall. Remember the middle term, multiply them together times 2, okay? So what I end up with here is 16 plus 8H plus H squared. That's how that multiplies out. Don't forget that middle term. Then I distribute negative 32 minus 8H plus 18. And then I have my minus 2 from the F of 4. Okay. Now I've got to simplify. So that the 8H minus 8H, goodbye. I have 16 minus 32. That's negative 16. Plus 18 is 2. Minus 2 is 0. So literally the only thing left is this H squared. Okay, and H squared over H, of course, is H. And the limit of h as h approaches 0 is 0. So that is the instantaneous velocity. The average velocity was -1. Okay, now it probably would have been helpful to look at like from 3 to 5 instead of 3 to 4 on the average velocity and then get closer and closer and closer. Well, we're not really going to have to do that anymore because now that you know how to find the derivative using the definition or the alternate definition, it's going to be easier to find the instantaneous velocity. And also, there are more ways to find the derivative, easier than this, that we will eventually learn. But the definition is something that you will see on the AP exam. It will be something you will need to reproduce yourself and show that algebra for. So that's definitely one that you need to know. Hopefully that was a good enough explanation and you can get working on 2.7 and have a great weekend.